some more MCQ in unit 2. So first one is using Chomsky normal form if a pass tree is generated. So we are going to generate a pass tree using Chomsky normal form. You know what is Chomsky normal form, right? In Chomsky normal form, you have a prediction as a variable tends to AB or a small a, two capital letter or a single terminal symbol. So the pass tree generated over here is always a binary tree. And one more thing is, like, when a pass tree is generated like this, so this is the possibility. You have all the nodes, and finally the end node will be a single terminal symbol. So all the branches will lead to a single terminal symbol. Okay, so this is the constraint, like always the end of the pass tree, it is a terminal symbol, and the interior nodes, it may have a possibility of two nodes or a single node. When I draw a maximum possible pass tree, then this is the maximum possible constraint for this. Okay, so this is Chomsky normal form, and this is the pass tree generated by a Chomsky normal form. Now what we are going to see, a word W. W is the sense, like, it derives to an input. So this is the input. Okay, so this is the input generated with no path greater than I. So we are going to take the length of the tree, like height of the tree with the maximum height, maximum path length. Then the length of word, like we are going to relate this I value with the length of word. Okay, so here all the paths are of equal length. So when I take this path, the length of this path is 3. The length of the path actually means that the number of edges actually connected. Okay, so the length of the path is 3. Then the word generated over here, the number of the leaf nodes. Okay, we can also call it as the length of the word, or the number of leaf nodes. The maximum number of leaf nodes are calculated using this formula. It is not greater than 2 power I minus 1. So here it is 2 power 3 minus 1, it is 2 power 2. So the maximum number of leaf nodes are possible is to the maximum of 4, not more than 4. Since the tree that I have drawn is all possible constraint, it works. Okay, we'll take one more length, like I can start with the length of, so I have taken length of 3 over here. When I take length 4, this is the pass tree structure. Okay, so you may have all the expansion, but the leaf nodes are single terminal symbol. It generates to a single terminal symbol. Okay, so here the maximum length is given as, sorry. So here the length of the tree is 4, 1, 2, 3, 4. And the maximum number of leaf nodes that is possible is 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here this is also like 2 power 4 minus 1, that is 2 power 3. 2 power 3 is 8. This is the maximum number of leaf nodes that is possible. Okay, so the formula that is actually suitable for this constraint is, it should not be greater than 2 power I minus 1. So we can take this option. Okay, so whenever you have a doubt, you better work it out. When you work it out for a simple example, you can find the answer better. Okay, so the next question is, Riemann normal form for the language. So a language is given and you're going to write a Riemann normal form for that. Okay, so it is really hard to find which is actually suitable. So we can neglect all those unwanted languages. Okay, so here the constraint given is, it is C power n d power n plus 1, and n value is greater than or equal to 0. So it actually means n value is greater than or equal to 0. So when it is equal to 0, n value actually ranges from 0, 1, 2 and goes on. So when n value is equal to 0, there is no C and only 1d will be there. And when n value is equal to 1, C power 1, D power 2. That means 1C, 2D, and it goes on. So number of C's when it is 2 and here it is 3. The number of C's is, D is 1 plus C. Okay. So this is the constraint. Now the minimum input taken over here is D. So we should have a prediction that regards to D. Okay, so here you have a single D prediction, here also you have a single D prediction, and here you have epsilon. But this language will never generate an epsilon. The reason is n plus 1, but even when n value is equal to 0, you have 1D at least will be there in the given example. So we can check this out. So this language, this is not the appropriate language for the given language. It is not the appropriate grammar for the given language. And we can go from this, the last one. Okay, so we can check whether it derives to any set of language with this constraint. So first we'll consider this D option. So D option is S tends to C, S, B or D. Okay, so here there is no prediction for D at all. And when you substitute S as D, it is CD. Okay, so there is no prediction. So this grammar is incomplete, so we cannot take this option. Okay, so we have checked out two options over here, and the last two left out are C and B. Let me take this option C. So option C, the grammar is S tends to C, S, B, and for B we have the prediction as DB or D. And what about S? S is incomplete, right? It is going to call recursively, and this S will never stop. So this grammar is also incomplete. Sometimes you'll end up in a grammar structure like this. Okay, some of the grammars might be a meaningless constraint. Okay, in that case, we can cancel it out directly. So only left out option here is B. So we check this B option. B option is S tends to C, S, B or S tends to D. So first a single D is accepted. And over here, this S is recursively called. So any number of time we can call this C, S, B and all. And S leads to D, and B also it leads to D. One single prediction for D. Okay. So always the number of D's is greater, 1 plus to the number of C's. Okay. So this is the perfect grammar that we are expecting. So the option answer is B for this question. Okay, so now consider this last question. Consider the statement, like two statements. So much of questions will be of the structure. Okay, so two statements are given over here. X1, the grammar. So X1 is the grammar. You have two grammars for X. You have to check whether they are not equal. Okay, the first statement is they have given two grammars and they said that both the grammars are not equivalent. So equivalent in the sense like they are not accepting same set of tokens. Always equivalence checks with the number of tokens it recognizes. Okay, so if for at least one input is accepted by one grammar and if it is not accepted by other grammar, then we can say that they are not equivalent. Any one grammar, any one input symbol. Okay, so we consider these two statements. So one is X tends to AXB, BXA, XXA. So this is for the first grammar, and the second grammar given is X tends to AXB, BXA and A. So these three are same. So we have to consider, we have to check whether this portion that is included here have any effect in the result or not. Okay, so here this X can be, X can be taken as XX, where I can substitute this X as AXB. If you don't want to go the complicated one, we can just directly substitute the single terminal symbol that is available over here first. Okay, so this X can be substituted with A and this X can be substituted with A. So this grammar actually generates a symbol AA, and here is there any way of generating AA? You have X tends to AXB. So when an A is there, then surely B will be there, or BXA. When A is there, B is also there, or a single A. So there is no possibility of generating AA to this symbol, okay, with this grammar. So we can say that this grammar generates this and this grammar does not generate AA. So we can say that this is not equivalent. Okay, so this X1 statement is true. The reason is the given grammar is non-equivalent. For one particular input symbol, one grammar generates it and other grammar doesn't generate it. Okay, so this is fine. And the next statement given is x2. X2 consists of two grammars again. Okay, so x tends to xx, exxx, ax, b, bxa, and epsilon. And here the next grammar is x tends to xx, ax, b, bxa, and epsilon. So this is the given one. Now the only difference between these grammar is this one. Okay, so you have this portion as x tends to triple x, 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 x. Okay, so for any substitution, if there is any variations available, then we can neglect it. Okay, so one I can give it as a x b. So since x is epsilon, we can give it as a b, b a, and a b. So we can check whether this can be generated using this statement. X can be generated with the a x b, and this x can be substituted with, I need b over here, so I can give b x a, and then I can substitute, I need one more b here, and give b x a, and finally you can give epsilon. So a b, b a, a b. So this is generated. Whatever is generated by this can be generated by this too. Okay, so it is going to generate the even number of a's and b's. Okay, and both the grammars are same. Whatever is generated by this variable for this grammar, this is generated by this grammar too. So here we can say this is equivalent, and the statement is also says that this is equivalent. Okay, so both x1 and x2 are same or correct. Okay, so the option here is B option. Both x1 and x2 are correct. Okay, thank you.